And it's recording, and I'm going to intro it now. Hey, what's going on, guys? It is Ryan at Exoderma and Exponential World.
Hey, how's it going, guys? It's Luke, and I'm also here with Ryan. We're going to talk today about some nice topics.
Yes, I'm going to say the topic that Luke just came up with, specifically. I'm going to start over. Hey, what's going on, guys? It's Ryan at Exoderma, Exponential World.
Hey, how's it going, guys? This is Lou, also from Exoderma.
Today we are going to talk about NBA2K. Not specifically NBA2K. It could also be FIFA, or it could be Madden. It could really be any video game that has any kind of like real world simulation, like modeling. And I'm going to sort of paint an overview of what that looks like and have Lou jump in onto what that actually looks like technically. So what we're talking about here is, like, you know, your game. You're playing FIFA, you're playing Call of Duty even, you're playing NBA 2K or whatever it may be, and you're moving a character on a ground in not real space, but some kind of virtual space in which you have to interact with the environment, right? And this is not something that you can, like, you don't just, like, draw a character and put it into an environment and move it around. There's actually math, and there's actually science, and there's technology that goes in to representing where someone might be standing on a virtual field or virtual basketball court, and then to have other people join that and then play a game on that. So, Lou, could you go over like what that technically looks like? What are we talking about here?
Yeah, so from a computer perspective, there's various hardware specifications that you need, right? That's why when you buy a video game or anything, they always tell you how much RAM you're going to need, what kind of processor you need. You need like all these different things in order to be able to run a game or a physics simulation in this case. One of the most important things that you need is RAM. So RAM is important because it holds the information that needs to be either displayed or accessed in order to do calculations on where the ball is going to be next, or, you know, what speed something is moving at. And all of this is done, all these computations are done by the CPU. So the CPU is what's getting, you know, a lot of the processing going, but there's also the GPU, and the GPU is going to display all the necessary pixel information. At the end of the day, it's an illusion, right? It's a very sophisticated, very genius illusion that there's actual people on the screen moving inside some 3D looking space. All of it is actually just colored pixels.
You mean that there's no one in a box?
Right. Contrary to popular belief, there isn't a huge stadium inside your TV. But what's really going on is interesting because the concepts are capable of being implemented due to object-oriented programming, right? So object-oriented programming is what gives you that ability to classify something as a player or as a ball or as something else, and then those things can be referenced inside of programs and interesting things done. So what's actually happening is I'm not sure if you're familiar with while loops.
With what?
With while loops?
No. While loops?
Yeah. So you have for loops? Yeah, so essentially a for loop is a type of thing you can use in coding to run through a sequence of elements. So let's say you have a list of 5 numbers, and you use a for loop. In your code, you'll go through each one of those numbers in that list, and some type of code will get executed each time that you run through those numbers. A while loop is a loop that...
While?
Yeah. A while loop is a loop that continues to happen over and over and over again with no specified stopping point. And that's pretty much what a physics engine is, right? A physics engine is something that keeps updating itself over and over and over again. And the thing that's getting updated is the information to display for each frame.
Yes. Okay. There's some connection there from programming languages and actually having like an environment that you have to constantly sort of. It's like maintaining the physical laws of that virtual environment, right? So if the ball's supposed to fall at a certain speed after it lands in the net, then this actual language is running the math to determine the ball and how fast it's moving. Now, does it actually know how heavy these things are? Does it have to know like mass or weight?
So the mass and weight are, I mean, without friction, there's no real difference in the acceleration, right?
That's true, yeah.
Yeah, so only if you're accounting for air resistance, then you have to account for the mass, and that would be added into like a differential equation that takes into account the velocity and mass.
So these game engines, like Unity, a physics engine, for instance, it has a fluid dynamics simulation equation. It has a simulation equation for elasticity modulus. It has a simulation, so elasticity modulus like rubber band guys, and then the fluid dynamics is like if you have water inside of a bottle, it's going to flow some specific way, and that's what these equations sort of model what it would look like. And so what you're saying is that these game engines have these rules that would dictate how something interacts with something else, these different classes of objects.
Yeah, exactly. They have different rules for how they get displayed on the screen. Pretty much, it's all about being displayed on the screen, or as it's referred to in computer vision, rendered.
So you have two parts. You have actually the doing of the physics, then you have the rendering of the physics.
Precisely. And the rendering is super important because you need a good GPU to be able to have a high enough frame rate so that the physics it looks similar to what it's in real life.
That's so interesting. So for instance, like when it comes to physics, it sort of models what I call the space-time, like partial differential equation, right? So it could be any combination of space and any time. So it could be like elasticity, it could be fluid, it doesn't really matter. Is sort of that. Wow. I mean, let me just dial back on that one right there because it's going a little bit off topic. So just to dial back to this whole video game thing, as far as modeling physics and redoing it, I'm trying to figure out what I'm missing here.
Yeah, so the physics environment or the game engine, it takes into account, like you said, all of these rules, right? These laws that Newton came up with and all these other smart people had figured out. Those equations just get implemented as some type of code. And then the objects inside of the environment can only follow those laws or those rules. I mean, unless you overwrite some type of code in there, and then you could do something like make something float, or make something, do something that's impossible in the real world, but possible in a virtual environment where you're pretty much a mini god, able to write whatever laws you desire.
Wow. So like So, and this applies to, I guess there's no limitation of what you can actually simulate. So we're not just talking about video games here. We're talking about movies, talking about anything that requires simulation. This is all literally done by math. Okay, so let me ask you a question. We're talking about video games. I watched on Netflix this documentary of Pixar. And Pixar is a pretty big popular name. I didn't know why. Now I know why. Because they're actually ones who popularized 3D animation. And they did it with these computers that were able to actually process 3D animations, and make these entire environments. These things also use math as well? Like literally use math to model in the computer. And so gaming engines have been around for how long? I'm still trying. Physics engines themselves. I mean, the physics engine is what we're talking about here, right?
Yeah, I'm not sure for how long. Probably since they started with the first shooting games, where you needed an agent inside of a 3D environment, something like that.
Yeah, that's interesting because, yeah, that's true. I mean, whenever you have to be able to do something predictive, you have to be able to implement the math via programming language.
Yeah, and there's also actually some interesting math that goes into the rendering aspect of it. So, for example, if you have the camera right in front of you looking at a certain part of the scene and everything else is not in view, there's no computation being done on that part of the scene. Like, there's no need to waste memory and space on rendering that part or computing anything that's happening in that space right now, right? Only when you turn the camera to that place does it start becoming computed. Does it start becoming like actually done anything to?
Oh, I see what you're saying. So you could have the whole environment modeled, but it's not actually being rendered until the camera is showing it.
Exactly, and that's how it saves a lot of memory and time, and it's super quick. Like multiplayer games, you can have a lot of people in different places of the map, in huge maps, because most of the map is not being rendered. The only thing being rendered is the immediate space around the player.
Wow, I'm thinking about like Call of Duty or.
Yeah, another math trick that they also use is to save memory and space is the detail of the objects around them. So objects that are closer to you are super high quality and detailed, whereas objects that are further and further away, their quality and their detail is actually purposefully reduced, so that you don't have to be rendering that quality from so far away and appreciate it.
So I'm sure that everyone like has seen the polygonal like representation of like triangles and people. Like so, like whenever you're displaying this stuff, we're talking about geometrical rendering, right? Like where like if it's a three-dimensional animation, it's because it's geometrical, it's geometry based. And so like in the really good engines, like I remember seeing a video recently, an advertisement for the new Unity engine of this new game, and they showed the triangles, a million triangles were in the image, but the triangles are more close together, closer to the person, to the camera frame. But the further you got from the further you got from the camera frame, the polygons are bigger. And it's not just like a modeling thing. It's literally for energy conservation, for a conservation thing.
Yeah, exactly. And all of that is mathematically computed and done in code, so that, you know, that's how they've structured it, and that's how they've engineered and architectured games.
Yeah, and literally virtual. So these are what we're talking about here. Is video games are literally virtual realities.
100%, yeah, virtual realities. That's I guess where the term comes from, right? VR. And interestingly enough, we're trying to now get that whole concept of this huge computer with a GPU and a CPU and RAM into goggles.
You know what? I like this direction. You know, so one of my first obsessions was augmented reality glasses, and like I have like this bias towards AR over VR, but I do believe that they'll one be the same device. They'll be the same device, right? And if they are the same device, there's some way to put on AR and VR into the same device. Maybe they're not. Maybe they're different devices. It really like it's going to be incredible, because what we're talking about here is actually shrinking. Like, because you're talking about two different parts, right? One of them we know is going to happen on the cloud. One of them is going to happen on the cloud. Maybe not the rendering. Maybe the rendering can't happen. Like, so let's talk about that, right? You talk about two processing things going on, two processes happening. One is the actual representation of the physics themselves, the actual calculations of the physics. The second is the rendering of the physics. One of those is going to happen server side, right? It's going to happen on the cloud. Would you imagine that? I mean, my assumption is that would be the actual mathematical processing.
Yeah, I think the physics calculations themselves can be done very, very quickly on a CPU or anything that's, you know, relatively strong nowadays. The hard part is always the graphics displaying, because of the amount of pixel information. So remember, like a 1080p is 1920 by 1080. That's a couple million of pixels. So each second, a couple million pixels need to be calculated and rendered on the display. And that gets done by the GPU. So the GPU specifically that's its only job. Just focus on the displaying aspect.
So you're talking about some kind of either a hardware improvement or some kind of integration in between that is able to shorten the rendering time.
Yeah. So rendering time, it's always, you know, needed for fluid visual feedback. So that's always going to be important. And then the physics of it, the calculations that you're talking about, I think that for now at least, or the physics that's being done in something that's not like a particle simulation. Like a particle simulation, you actually, I don't think you could even run it in real time. I think you have to let it pre-process for a couple hours or days, and then you can play the video back in real time after that whole couple of days of processing. So as far as like a real physics simulation goes, I don't think we'll probably be able to get that running because of the complexity of the calculations.
Like, hypothetically, quantum computing happened, right? Now we're able to store colors and colors or pixels within quantum bits. You know, is this a method that could be used to shorten the processing or make it more efficient so that way rendering would happen faster or make it, you know, less energy consumptive?
Yeah, man, 100%. I feel that that's one way to go. Another thing that we can try to do is figure out how the brain is doing it, right? How is the brain integrating all the information it gets from all the billions of neurons, and how does it render it right onto your experience? And
so in our heads, the virtual reality is what you're saying.
Yeah, exactly. And you're updating how many times a second, right? I don't. That's a question I've always had. I've always wondered at a frame rate does human experience refresh at?
It's like 36,000. I thought it was like super high compared to anything we have. Let's just Google it though to be sure. What would I technically look at? Are we looking at a frame rate in our eyes, or are we looking at brain refresh frequency rate or whatever?
That's a hard question. I'm not even sure where it would be located in. It's a hard question to think about.
Frames per second. Someone typed it in. Let's see. 10 to 12 images per second. 28 to 24 to 48 FPS. That's not what we're talking about. FPS. 144 hertz. That's what humans can see as far as wavelength.
Yeah, I don't think this question has been really asked.
What are we asking exactly? Let's figure out what we're asking. So that's what it seems to be the...
Yeah, I was talking to my brother about this actually the other day, and I broke it down like this. I said that, think of a moment, right? One moment. You take a place in time and you freeze it. And you take all the stuff that you can appreciate in that moment, like the visuals, the colors, the geometry, and that's one frame, right? That one moment is a frame. But life doesn't occur, like, you know, in that way. It flows by seamlessly. So my question is, how many moments are happening each second that you're aware of?
What you're talking about would be the physics in between electronics and the biological electronics. And, I mean, the physics of biological electronics, so it sounds like literally literally turning what we have as math and somehow reverse engineering and figuring out. Like, there is obviously an electrical refresh rate. There has to be because it's electricity, right? The question is it a continuous stream? There is no frame? What if there is no frame? What if the processing is happening? Like, I can't even say. What if how do you even, like, I can't conceptualize it. It's so abstract. I can't conceptualize it. What if there is no frame?
Good. That's an interesting question I never thought about. What if it is continuous and it's not discrete?
Well, one of my friends who works on machine learning at, like, another facility, a university, he one of his theories is that maybe some of the processing happens in the organ itself, right? Now, there's no way to really know, but what if, like, the visual processing itself, the image is put together in the eye, not in the brain, right? So that would mean the brain does something else with the image. Or maybe, like, the brain does have, maybe the nose processes some of the smell before it gets to the, maybe there's, like, I don't know, obviously there's no way to really know yet, but.
Yeah, so I do think that the eye and, like, all the other organs that we have do some pre-processing on the information. So they do some basic filtering, they do, like, some interesting things, so that it becomes more of a signal that the brain can interpret. But yeah, the question that we just asked was pretty insane. And the thing that could go along with it is how many megapixels or gigapixels of resolution do our eyes have? So that's another question.
Human sight resolution, something like 576 megapixels.
That's pretty big. Jeez.
That's it. That's quite large.
Yeah.
Wow.
So is that for each eye?
I imagine it changes per person, but I don't know. It is. Let me see if I can find something more specific. LASIK MD. No, I don't need LASIK.
So yeah, imagine how much quality, right, is in a single image that our eye picks up, and then we would have to figure out how many images are refreshed each second in our brain, and we could get an idea of how much processing actually goes on in order to display it to
You wouldn't know how it does it. You'd just be able to know how much information is going through.
Yeah, 100%. And how it does it would have to be more studying into like the neurochemistry and
No, so my mind, like the rods, the cones, the iris, and the stretching, those are all filters. Like if you were to take a camera and you were to layer over contrast or layer over vignette or whatever you want to lay over, that's what our eyes are there. So it's a structure that has other structures that do function. So the structure of the eye itself has a function, seeing. The structure of the eye is composed of other structures that have functions that enable seeing. Cones, rods, iris, the muscles that contract your iris, obviously. I'm sure there are other things that I can't think of. I don't know. But like, just imagine, like, those are all like, man, this is so crazy to really think about.
That's why I've actually had the idea that if we're going to find a solution for robotic vision, it would have to be both a hardware and software solution implementation because of that. The fact that, it's just so much pre-processing that goes on before the light even passes into your retina.
It's so much, like it really is, because like there's the light, the external stimuli doesn't change. It's the same amount of external stimuli. What changes is how my body handles the external stimuli, right? So our eyes are changing based upon the external stimuli. Like the external environment, the lights continue it. Like that's so crazy to think about, because it means the human eye is really good with color vision, right? But there are other species that have eyes that do things that are much more specific and in some contexts much more useful than the color vision that our eyes have. Now, I will admit that primates have the most developed color vision of any species, and it's helped us, they theorize, it's helped us to avoid certain poisonous insects and animals because the most colorful are generally the most poisonous. But man, it's crazy to think about this from a technical perspective. Like we're talking about well, to me it's biomimicry, which I love, which I'm like, that's what we're talking about here. It's literally, so we went from video games to modeling physics within a virtual reality to biological hardware that models physics in a virtual reality.
Yeah, man, we're doing it. We're doing it already. How we're doing it, or how it became possible to do these things. That's definitely up for another podcast.
Yeah, touche. Touche. All right, so that's a good point. We're gonna mark it here, end it, because it's as you guys can see, the things that we've chosen to talk about have so many layers and they're so complex, but they're so beautifully simple at the same time. Like the end result of NBA2K or FIFA, it's so beautiful in the impact, but the mechanics that go into actually build something like this are so complex, and they're so complex. But anyways, we're gonna end it right here, and we will see you guys in the next podcast. Lou, what you got to say?
Yeah, man. Closing remarks are definitely that there's some type of insane phenomenon, right, happening. Let's take apart our head for just 1 second, right? So your eyes are the hardware that is able to receive the light, and then there's another piece of hardware, your brain, which is taking that light that's being received and it's processing and interpreting it as what it is that we see, right? What it is that we're living in this apparently spacious, colorful world. Now, imagine trying to do that for a robot, right? Like you get robotic eyes, and then you get the brain CPU trying to integrate all that information so that a robot could possibly experience also vision or something. I'm not sure if we'll get there because I'm not sure we understand how it all gets done by the brain, but that's maybe one of the hopes of the people in the future that listen to this podcast and want to continue our work or something. So
yes, I could have said it better. That's exactly the intention. So if you guys have any specific questions, comments, you think that what I said was stupid, let us know, and we will get back to you immediately. In the meantime, leave comments. Thank you guys for tuning in.
Take care, guys.
Take care, guys.